Welcome to the deep dive. We get you informed fast. Okay, imagine this. The digital security we rely on every day, for banking, messages. What if its foundations weren't quite as solid as we hope?
Mm-hmm.
Now flip that. Imagine quantum computers not just breaking our codes, but actually building stronger ones.
Yeah, that's exactly where we're headed today. We're diving into some really quite surprising new research.
Research suggesting quantum cryptography might be fundamentally resilient, maybe even if classical methods start to, fail.
Precisely. Our mission today is to unpack this groundbreaking paper. It's called Founding Quantum Cryptography on Quantum Advantage by Karana and Tomer. It really shifts the landscape, suggesting quantum crypto could, really thrive and keep things secure, even if the classical world gets shaky.
Okay, let's break this down then, because to really get this, we need to understand the classical picture first, right? The challenge it's solving. For ages, nearly all our modern digital security, classical cryptography, has relied on something specific, these one-way functions.
Right. Think of it like mixing paint. Super easy to mix red and blue to get purple.
Yeah, easy enough.
But try getting just the pure red and pure blue back out of the purple. It's, well, practically impossible.
Okay, so that's the one-way idea. Easy forward, hard back.
Exactly. Classical encryption uses math problems like that. And for a long time, the assumption was that even fundamental quantum tools, like, say, bit commitments.
Those digital envelopes you mentioned, where you commit to something secret?
Yeah, those. We thought they'd need similarly strong, hard-to-reverse assumptions, based on those classical one-way functions.
Which brings us to this concept, microcrypt. Sounds a bit sci-fi.
It does a little. Is this hypothetical idea. What if quantum cryptography could work, could be secure, even if those classical one-way functions didn't exist or were broken?
A world without that classical bedrock, but still having quantum security.
Exactly. And what's huge about this paper is they provide the first unrelativized constructions.
Okay, unrelativized. What does that mean in simple terms?
It means they've pulled it out of the realm of pure theory, like these abstract oracle worlds mathematicians use. They've shown concrete ways this microcrypt world could actually be built. It's not just a what-if anymore. It's potentially real.
Wow, okay. So if microcrypt could be real, where does this quantum security, this resilience actually come from, if not the classical stuff?
Well, this is the really interesting part. The paper argues it's built on mathematical assumptions that are, perhaps counterintuitively, weaker than what classical crypto needs.
Weaker? How does weaker make it stronger?
It's a different kind of hardness. They're talking about problems believed to be in a class called #phard. You don't need to worry about the label, but basically, think of these as problems that are so complex, they're thought to be much harder than even the standard one-way function problems. Way harder.
Harder like estimating outputs from complex quantum systems, that sort of thing.
Precisely. Things like approximating the permanence of certain matrices or the output probabilities of random quantum circuits. Stuff that's really, really tough for classical computers.
Okay, I think I'm starting to see the connection. This hardness links to what quantum computers are supposed to be good at anyway, right? This quantum advantage.
Yes, exactly. That's the key link. Things like boson sampling, random circuit sampling, tasks where quantum computers are expected to massively outperform classical ones.
Not breaking codes, but generating patterns that classical machines struggle to mimic.
Right. And the paper shows this amazing connection. The difficulty for a classical computer to even simulate these quantum sampling processes. That difficulty itself can be the foundation for quantum cryptography.
So the very advantage of the quantum computer in doing something becomes the basis for security against a classical attacker trying to undo it.
You've got it. It's a shift in perspective.
So what's the actual building block they propose using this idea?
They call them one-way puzzles. It works like this. A quantum process, the sampler, spits out a pair of classical pieces of information, a puzzle, and its key. The security guarantee is that, thanks to that underlying quantum hardness, no classical computer can feasibly figure out the key just by looking at the puzzle.
The quantum part makes the puzzle easy to create, but hard to solve classically.
That's the essence of it.
And they prove some deep connections here. Equivalences.
Oh yeah, this is profound. They show that several seemingly different concepts are actually equivalent under quantum reductions. It's like finding a hidden unity.
Such as?
Well, they show that the hardness of classically approximating those quantum outcome probabilities we talked about is directly equivalent to the existence of these one-way puzzles.
Okay.
And if you have these one-way puzzles, that implies you can build things like quantum bit commitments and even secure multi-party computation, the foundational tools.
So hardness assimilation leads to puzzles, leads to secure primitives.
Exactly. And it goes further. It connects to things called state puzzles, where it's hard to create a specific quantum state just from a classical description. Even certain types of quantum money schemes fit into this picture, implying the existence of these puzzles and bit commitments too.
Wow, so it all ties together. The big takeaway then is microcrypt isn't just a theory, it looks like it could actually be real.
That's certainly the strongest evidence we've seen. It suggests the bar for quantum cryptography might actually be lower, in a sense, than for classical crypto. We might need less hardness, but a specifically quantum kind of hardness.
That's fascinating. So connecting this back to you, the listener, what does this mean practically?
Well, it suggests that the foundations of quantum security are being rebuilt on assumptions that might be more robust, tied directly to the power of quantum mechanics itself. This isn't just theory. It could mean a future where your sensitive data stays secure, even if, hypothetically, classical encryption methods hit a wall.
A future where quantum keeps secrets safe, potentially independently of classical methods.
It opens that door, yes.
So here's something for you to think about. Imagine that future. Our current encryption fails, maybe due to advances in classical computing or math, who knows, but quantum cryptography holds. What new challenges, what opportunities arise in a world secured by fundamentally quantum rules? How does that change your digital life? Something to chew on.